my dissertation called Interactive Learning of Dynamic Systems, a Cognitive Modeling Approach to Mental Model Building and Updating. So first I want to give you an overview of today's talk. I'm going to talk about the motivation and the background, then introduce the first and the second studies, which I conducted using smartphone apps, and then the third study, which is a dynamic decision-making study, and then give a summary change. So if you have a new app, how do we know how to use it? How do we learn to use unknown systems? Is it that we read a manual, or is it just a learning by doing? Do we just try it out? So what it is interactive learning. It's learning by doing. We build upon our previous knowledge that we have acquired with other similar systems. We dynamically adapt our decisions on what to do next depending on feedback, and we update our mental model. So how does this happen? What exactly is mental model updating? So Lee and Mani propose mental model updating as conceptualization, experimentation, and reflection. So and this is a SIR cycle, and in the conceptualization phase, people have some kind of idea how something works, and they try this out in the experimentation phase, and then they get feedback from the system, and if it's positive feedback, they just keep their concept, and if it's negative feedback, they reflect on their concept and they rebuild it. What's also important is as mental models evolve, they become more specific, and mental model building and updating also requires metacognition. So what is metacognition? Metacognition is thinking about one's thinking. It's knowledge about when and how to use particular strategies for learning. And so the question of my thesis is, how can mental model building and updating during interactive learning be precisely specified? So one method that is very helpful here is cognitive modeling. Cognitive modeling requires the researchers to be explicit about a theory in a way that verbal theories are not. So important features are using formal language, explaining cognitive processes, and building upon the principles of cognition. And advantages are that you have precise quantitative predictions and the models are generalizable. So one modeling approach that allows to model cognition as a whole is using cognitive architecture. So cognitive architectures model different cognitive processes together. And cognitive architecture that is useful for modeling interactive learning is ACT-R, Adaptive Control of Thought Rational. So with ACT-R you can also model actual system interaction. There are ACT-R modeling approaches for microworlds, and ACT-R is very good for modeling learning processes over time periods. Now, what exactly is ACT-R? ACT-R represents the attempt to achieve a unified theory of cognition. This means that finding different theories of cognition are computationally implemented in ACT-R, and ACT-R also has a modular structure which resembles our brain. So if you look at this image, we can this is symbolizes the modular structure of ACT-R. We have different modules that process different types of information. So we have a declarative memory module for our long-term memory. We have a imaginal module, which is important for learning things by binding new information together, visual modules, modules for motor activity, and other modules. And ACT-R works by using rules and mechanisms. And the rules specify which information and which modules is active and how this information is then changed. And the mechanisms are also control how the model runs. So now I hoped I could show you that ACT-R is the architecture that we should use when we try to model mental model building and updating for dynamic systems. Now, how do we know that the model that we are developing with ACT-R is a good model? So first of all, we have to keep in mind all models are wrong, some are useful. So usefulness would be one criteria for a good model. So usefulness could be from an engineering perspective, that it helps you develop tools for understanding cognition, or also it looks at novelty. The model it has a novelty contribution to science, and then it's also good if a model can describe data. That means that you have empirical data with effects, and the model can match the effects found in the data. And the model should also predict data. That means that you have a model, and the model predicts effects that you find in empirical data. And finally, there's the prescribed criteria. That means that the model should be a generalizable model so that it can predict behavior in different situations. Okay, so my main research question is, how can the mechanisms of mental model building and updating be implemented with ACT-R so we have a good model? And further research questions are, can a model based on these mechanisms describe data of an interactive learning task? Can a model based on these mechanisms predict data of an interactive learning task? Is this model useful for evaluating the usability of systems? Can the mechanisms be transferred to settings, contexts different than those they were developed for? And finally, is this model useful for describing dynamic decision making? Now, on this slide, you can see an overview of my research questions and how they are looked at in the 3 studies of the dissertation. So in the first study addresses the first research question, if the developed mechanisms can describe data of a study. So this first study was a study done with a shopping app. Here empirical data was collected and a model was developed that implements mechanisms of mental model building and updating. And now for looking at if these mechanisms can predict data, a second study was designed. This is the real estate study. Herefore we have the same model was used, and it's looked at if this model can predict data. And both studies 1 and 2 are important for looking if these models is useful for evaluating usability of systems. Then to look at if the mechanisms can be transferred to different settings, a third study was conducted, and a different model which uses the same mechanisms was developed. This is the dynamic decision-making model, and it was looked at if this model is useful for describing dynamic decision-making. Okay, now let's look at the app studies and the model approach. So the motivation and requirements for the app study were, first of all, to model mental model building and updating in accordance to the Sur cycle of mental model updating by Lianmani. The task should be learnable so we can observe mental model building, and to study mental model updating, the system needs to change to some extent. And the users should be able to use their previous knowledge in the beginning, thus the content of the system should generally be well known. And finally, the task and the system need to be realistic, but on the other hand, they should be manageable. So we should be able to build an ACT-R model. And finally, the data should allow for prediction of usability. Now, what exactly is usability? Usability is defined as the effectiveness, efficiency, and satisfaction with which specified users achieve specified goals in particular environments. And important criteria are effectiveness, efficiency, and satisfaction. So effectiveness means how accurate and complete the goals are achieved, and efficiency means how few resources can be used, so how fast the goals can be achieved, for example. And satisfaction is more about how comfortable and acceptable the system is. So the first 2 criteria are probably easy to quantify, and the third, I would say, is more difficult. And this is important because the general idea is to use cognitive models as a substitute or supplement to user testing. What this means is that we reduce the number of test subjects, we decipher underlying cognitive processes, and then we can reuse the models for similar applications, and this way predict usability. Already other people have worked on usability prediction with ACT-R models. There is, for example, the Cocktool approach, which can predict expert user behavior on websites, and Cocktool Explorer can also predict novice user behavior on websites. There are also studies which look at how menu search and mobile phone usage goes along, and how this can be modeled with ACT-R. However, there are no models for learning and relearning in a usability context with ACT-R, and also there are no models for the users of smartphone apps. So in the first study, we designed an app that was a shopping app, and the participants were supposed to search for items and select them, and the shopping list was dictated to them, one item at a time, and then they had to select the items. So this is how the app looked like. So you see, it's a hierarchical linear app, and they had to click through different layers to look for the target, which was in this example alcohol-free beer. And there were two versions of the app, a 3-layer and a 4-layer version, and the participants had to repeatedly look for the same 9 items, and after 2 blocks, so after looking for the same 9 items 2 times, there was an uninformed switch, so they switched to the other version and again looked for the same items for 2 times. And half of the participants started with the 3-layer version and the other half with the 4-layer version. Okay, now this study was done to look at if these mechanisms can describe the data, and I'm going to talk about the model fit in a minute, and afterwards I will show you the model. And there was another study which was designed to look at if these mechanisms can predict data. And this study was done with the real estate app. Now the real estate app looked similar to the shopping app, however it varied a bit. It's an adaptive app, and other than this smartphone app, the shopping app, some of the positions of the items changed, not all of the positions, and also depending on pre-selection, some of the paths leading to the targets changed. The design, however, in this was quite similar. They had to look, there were also 4 blocks where they had to look for different criteria for real estate search. And now let's look at the data. So we have here an overview of the data of all 4 studies from the real estate app and the shopping app, and the dependent variable is always the average item selection time over in 1 block. And we have here the empirical data and the model data, and then we have the switch that's the same. And I'm just going to explain you the data for one specific study for the shopping app, the study 3-4, so they started with the 3-layer version and then switched to the 4-layer version. So this is the empirical data, this is the model data, and we see in the empirical data there is a decrease in selection time from the first to the second block, then an increase again, and then again a decrease, and in the model there are the same general effects. However, the model learns faster, and the model here has an R-square of 0.799, and the RSME is 1.489. This is the worst fitting model. If you look at the other studies, the best R-square is the one I fitted the data to is 1, and RSME is 0.011, and these are the other 2 values. Okay, now let's look at the findings on usability. So first of all, you can measure efficiency as a time on task. So you can look at how fast can items be found, and measurements of efficiency are always relative. So if you just have this value of time, this doesn't really help you. You have to compare different apps. And then what is also important, learnability can be seen as the decrease in time on task, and this model can be used to predict task time for other apps with a similar structure. Okay, so now let's look at the model finally. So first I'm going to explain the app model and then look at the general model mechanisms for mental model building and updating. So the app model has 3 important parts. First of all, in the beginning, the model uses basic knowledge or previous knowledge, and it then builds up more elaborate task-specific knowledge, and it also has metacognitive control mechanisms. So let's look at the basic mechanisms first. So the previous knowledge of the model is stored as association chunks. So the knowledge that you have that alcohol-free beer and beer is related, or that alcohol-free beer and bottle shop is related. So the model already has this knowledge, and it retrieves it from its declarative memory. Now, as the model interacts with the app, it builds up more specific task knowledge, and this is stored in the form of a representation chunk, which is built in the imaginal module where information is bound together, and these can later be retrieved from declarative memory, and they become also more specific as learning works. So these representation chunks are kind of like paths which show you, if I'm looking for alcohol-free beer, I have to go to bottle shop, and then I go to alcohol-free beer, or as you learn, okay, there are two different versions. You have a specification here, and then the path chunk has more slots. Okay, so in the conceptualization phase, basic knowledge is used in the beginning, and then elaborate knowledge is built, and the general mechanisms is the representation chunks, where the situation part A, situation part B, part C is encoded, and then the predicted outcome, and there is a specification. Okay, now let's look at the metacognitive control mechanisms, which first for the app model and then in general. So we have three mechanisms, one for environmental changes, one for changing of established strategies, and a retest mechanism. So we already have the representation chunk, but what we also have is a control chunk, which is held in the goal buffer of the model, and it has two slots, one for uncertainty, if the model is not sure about what it is doing or what is happening, and one for if the model has registered environmental changes. And so if you have, now I'm going to explain you the retest mechanism. So the model is using a representation chunk. It is already has looked for alcohol-free beer, has a path, and uses this chunk, and then it's expecting to find alcohol-free beer, but it doesn't. It has unexpected outcome, and then it will note, I'm uncertain in the control chunk, use the representation chunk again, and if it again achieves unexpected outcome, then it will note, okay, there's something changed in the environment, and then rebuild the representation chunk. And generally, this is something that happens in the reflection phase. There are the reflection mechanisms for environmental changes, for changing of established strategies, and also retesting them. Now let's look at the dynamic decision-making study. So the questions are, can the mechanisms be transferred to settings, contexts different than those they were developed for? And also, is this model useful for describing dynamic decision-making? So the motivations for the study was looking, we need a broader scope for the developed modeling concept, different interactive tasks, stimuli and setting, and also the task needed to include mental model building and updating. So the chosen task was a task where participants were presented a tone, and then they had to press one or two buttons, and then if the button was correct, they got positive feedback. If it was wrong, they got negative feedback. Now, why is this a complicated task? Because we have 160 different feature combinations, and they differ in duration, direction of frequency, modulation, intensity, frequency range, modulation speed. And there was positive feedback only for specific combination, so for loud, high, and one. And the task went on for 240 trials, and after 120 trials, there was an uninformed switch of button assembly, so now they got positive feedback for loud, high, and zero. Okay, so this task is an example for dynamic decision making, which means we have a series of decisions. The decisions are dependent on feedback on previous decisions, and decisions are made under time constraints and the environmental changes. So typically this is modeled using instant-based learning. Hereby instances are built, retrieved, evaluated, and reinforced during interaction with a dynamic environment. So we have the situation encoded as a set of attributes, the decision and the action, and the value for making decisions in the situation. However, in this task we have these uninformed switch, and for this we need some specific rules. So the model for this task consists of exemplars or instances which encode the strategies as feature value pairs. then specific rules for switching the strategies, and the metacognitive mechanisms for environmental changes, for changing of established strategies, and the retest mechanism. So the examples are the strategies, and they are stored in the representation chunk. So we have a first part of the situation as first feature value pair, the second part of the situation as the second feature value pair. So the first one would be duration short, the second one would be volume high, and then we have the predicted outcome, and then this would be the response. And now we have a specification if it's a one or two feature strategy. So what I forgot to say, that in the beginning the model will use one feature strategies, and later on switch to using two feature strategies. And so for switching between strategies, there are explicit switching rules. For example, if the current strategy is a one feature strategy that was successful often, but it caused an error before, then retrieve a two feature strategy, which includes the current feature value pair and the response. And there are other switching rules, for example, for switching between different one feature strategies. Now, the metacognitive control mechanisms are, as you have seen before, they are for registering environmental changes, for changing of established strategies, and the retest mechanism. So we have the representation chunk with the strategy, the control chunk for noting uncertainty and environmental changes, and we have a strategy which leads to unexpected outcome. Then we note in the control chunk that we're uncertain about this strategy. We try it again, you get unexpected outcome, and then the control chunk will note, okay, something has changed in the environment, and the representation chunk is rebuilt. Okay, so these are the reflection mechanisms used. So how good does this model fit the data? So what we have here is the straight line is the empirical data, and the dotted line is the model data, and also we have a large variance in the model and in the empirical data. So generally in both data sets we have the proportion corrects the dependent variable, so we have participants get better, increase in the direct proportion, and then after this uninformed switch there is a drop in performance, and then participants and the model get better, but there are differences. First of all, the model is worse than the participants, and the model takes longer for recovering. However, the main effects are in the model. Okay, so now let's sum up and give an outlook. So the first question was, can a model based on these mechanisms describe data of an interactive learning task? I think it can. The second question was, can it predict the data? It can. And is it useful for evaluating the usability of systems? I think it's very useful for usability prediction. And now about the dynamic decision-making model, the questions are, can the mechanisms be transferred to setting contexts different to those they were developed for? So the same mechanisms were used and a new model was implemented, so yes. And is this model useful for describing dynamic decision-making? I think the model describes average data and also variance, and for the first question, the prescribed criteria is met. Now, the main question was, how can the mechanisms of mental model building and updating be implemented with ACT-R? So what we have is a representation chunk in the conceptualization phase, where situations is encoded as part A, part B, the predicted outcome, and there's also a specification as learning evolves. And then we have in the reflection phase, we have different metacognitive processes for registering environmental changes, for changing established strategies, and a retest mechanism, and we have the control chunk, where uncertainty about the representation chunk and environmental changes are explicitly registered. So now I want to discuss strengths and weaknesses of the general model approach. So first of all, the strength mental model building and updating was modeled in accordance to the SIR cycle, and it was implemented in ACT-R. And an app model with these mechanisms can describe and predict data, and a dynamic decision model with these mechanisms can also describe data. Now, what are the weaknesses? First of all, the change mechanism. So in this model, or in the mechanisms, it's always it tests established strategy once and then again after 2 errors before it's discarded. And I think this is a quite arbitrary value. It's maybe a rule of thumb, but you have to look at the task. How well is this strategy established, and maybe make this more adaptive. Then there's the feeling. I encoded the feeling of uncertainty as an explicit value. I'm not so sure about that. Also, if you have more complex systems and you want to represent the mental models of these systems, then you need more than one representation chunk. And I use the goal module for metacognition. I think there should be a specified metacognitive module for that. Okay, now for the strengths and weaknesses of the dynamic decision-making study. The model can be transferred to other categorization domains. For example, we can use visual stimuli instead of auditory stimuli. Then the main trends are captured by the model. Average behavior is captured by the model, and also the model can simulate the large variance we found in the empirical data. The weaknesses are it's actually unclear from the empirical data which strategies participants follow at every point. And then we don't really know if individual strategies are captured by the model. The model uses these many switching rules, and we don't know if they're necessary and if they're adequate. Now for the app study, the strengths are the model describes and predicts average data. The main trends are captured by the model. Usability prediction of learning and updating effects is possible with the ACT-R model, and the model can also be changed for other apps with a similar layout. However, the data that we use is limited. We only have average data over many items and not item-specific data, and also the model uses only mouse instead of touch commands. Okay, so now I'm going to give an outlook. First of all, for the question, can we achieve automated usability testing with ACT-R models? For this, we would first have to develop different modules for different types of apps, and then during my thesis, we also developed the ActDroid tool, and this tool allows ACT-R models to directly interact with Android apps, and this is very helpful because you don't have to write a prototype of the app, so the ACT-R model can directly work with the app. And now we can also use ACT-Touch commands, so we can model actual touch behavior. Okay, now for the second outlook is about the dynamic decision-making model, and maybe developing cognitive intelligence systems. For this, we would have to improve the dynamic decision-making model. We could do this by collecting empirical data and also changing the paradigm a bit so we can be sure of which strategies participants follow, and then we can write a model that actually follows the same strategies as the participants, and then we can design a cognitive intelligence system, so a system that simulates the cognitive processes of the users that emerge during system interaction. And such systems are always informed about the cognitive state of their users, and they can then help users make better decisions. Okay, so I'm finished now. I would like to thank you and